Good morning to all of you. Myself, Professor Mayur from Paramilitary Technical Campus. Yesterday we started the design of plate girder. In the theory part we have completed. Also some total provisions are seen as per the IS 800 2007. So for your guidance, you need to be your IS 807 guideline for the design. Okay. There are some correction that BIS list of correction I have also shared with you on your WhatsApp group as well as on your classroom, so you can benefit from there. Okay, so IS codes are very important. Uh, you can't design without assistance of that code. So you should go through that code and also understand the problem, how to solve it. Okay, so yesterday we have started the plate girder example. We have seen yesterday the theory, codal provisions, also uh, the plate girder made with the different components of the plate girder that are flange plate, web plate, longitudinal stiffener, transverse stiffener, and post stiffener at the end for the reactions, and intermediate transverse stiffener when there are point load on the plate girder. So we have seen yesterday, and I also started one example of the plate girder with a span of 36 meter, span of 36 meter. Okay, and about the loads are also given dead load and live load. Only for the gravitational load you have to design. That means no dynamic loading on such a on the girder. And then there are factor load to calculate for the case of UDA and the concentrated load, gravity loads. Okay. So after load calculations, we have find out the maximum shear force and maximum bending moment for the design. And the basic assumption we have yesterday that the flanges they will take care of flanges they will take care of the bending moment. The flanges are at a distance d apart, and the web of the plate girder they will resist the shear. If it will be uh, if flanges they are not able to take the bending moment, then additional stiffener are provided and they are called as longitudinal stiffener. It is okay. Or maybe to increase the thickness, you can provide the splices to the flanges web. That is the web splice. It is called okay. This is web splice. Or in case of if you are this web is spliced when shear is large and your web is not able to take out. And also the stiffness are provided at the end or intermediate to overcome uh, uh, large forces, and to bring the our uh, design in safe condition. So here we have yesterday seen one example started, and we find out the depth of girder. We have decided depth of girder. Also the empirical equations are there. You can use this empirical equation to find out the economical depth, which is given in the Instructorium book, and then you can find out the area of your flange required. Okay, so that is the case. And then width of flange you can assume with 0.3 times of depth of the web. That is depth of web already you have decided, that is 2.6 meter. So width of web you can find out, that is coming 780. If you take the 780, then you can find out the thickness TW, thickness of flange required, not TW. Here, sorry, make the correction. thickness of flange required you can find out because area of flange you know and width of flange you know. So by this you can calculate and then approximate selection of the thickness of the flange. Then area provided for the flange you can find out and then compare with the area required. Okay. Then the section classification because we already decided the size of flange fillet and side of fillet, so section classification can be done. And based on after the section classification, we have come to know that flange is plastic, but sorry, flange is plastic, but wave is cylinder because the depth of section is too large. That's why the wave is cylinder, and then wave is also required for the check for shear buckling because the D by TW ratio is more than 162.5 and which is greater than 67 epsilon, which is greater than 67 epsilon. So that is we have uh, then up to this, then we have based on the serviceability condition, we have checked for the TW, that is thickness of web you have chosen, it is safe or not. In serviceability condition, TW we have find out it is coming 13 mm, which is less than 16 mm, and so we can go for that. So then the initial sizing of member is done. That is the dimension of flange plate. Initial sizing means the dimension of flange plate and dimension of web plate are decided. Are decided. Okay. So that's why this is up to this we have initial sizing of member system. Okay, and also we have chosen the first panel spacing of the your plate girder, and that is we have taken the center to center distance for the first spacing is C is equal to 2500. Okay, and then based on that C by D ratio, we have checked the serviceability condition. Okay, then the moment of resistance we have to find out. We know what is the moment. Then moment of resistance because our basic assumption is that the your flanges they will take care of flanges they will take care of your bending moment. So this assumptions already we have discussed yesterday. So taking care of bending moment and resisting bending moment due to transverse loading. So you can find out the bending moment, that is MD, or MR, you can say resisting bending moment, or let's say resisting bending moment. Because two flanges are there having a distance of D, uh, that is center to center distance is the flange plate. You can say AF into FY into D divided by gamma MO. I think so. This will be the your bending moment for this case. So you know that this I section you can say in our case that the center to center distance is nothing but uh, the the thickness of flange plate is 50 mm. Here also 50 mm bottom plate, and the depth of this depth of wave is 2.6 meter or 2600 mm. So if you find out the D, the center to center distance between the flange plate, D is equal to it may be 2.6 meter plus 50 mm divided by 2 plus 50 mm divided by 2. So I will write down all the mm. So 2600 mm I will write down here. Uh, so here you can write down this I will erase, and this is 2600 mm. So it will be coming 2650 mm. Okay. So this already moment of resistance we have find out the area provided we have to take here 39,000 into Fy for all the material you have taken. Yield stress of steel 250 Newton per mm square with the partial safety factor gamma MO. Gamma MO is 1.1, and the depth we have find out center 50. So we have get this some value of this moment of resistance, that is 23488, 23488.6, 23488.63 kilonewton meter. That is the MR, and you can know that MR is greater than MU. MU is 20701 kilonewton meter, as we have calculated earlier. As we have calculated earlier, 20709. Sorry, 20709 kilonewton meter. So this one is larger than. So you can say that the MR is moment of resistance is okay as per the factored moment. Nu is the factored moment. Uh, you have calculated factored moment. Calculate. Calculate. Okay. This already we have done. Okay. Then we have proceed. The our plate girder is 36 meter long. Our plate girder is 36 meter long. Point, point V. Okay. So RA we can say. So total length of this plate girder 36 meter. So because of symmetricity, simple joint at both sides. So what we will take? What we will take? We will take the half portion only, and this half portion uh, of the braid girder we will divide with the number of panels. So why we are going for the dividing the number of panels? So because here in our case when we find out this d by tw ratio, you can see here d by tw ratio we are finding 162.5. So in our case d by tw ratio is equal to 162.5, which is greater than 126 epsilon, and the section is cylinder. एक तो ये हो गया. Okay, cylinder section है तो we have to spin and we have to provide this signal. Also it is greater than 67A, so that is the check for shear buckling check is required, because these clauses are given. Shear buckling check is check is check is required. So that's why what we are doing, we are dividing our plate girder into numbers. Divide, divide, divide plate girder, girder into panels. So we will divide the different panels. So first panel we will take first panel. Over here you can see we have divided the number of panels. You divide the number of panels such that it will be symmetric. Okay, so you can see that. So this is the panel 1, panel 2, panel 3. Okay, panel 4, panel 5, panel 6, then 7, 8, 9, 10, and 11. So 1 and 11 having the same dimension. Okay, 2 and 10 having the same dimension, 3 and 9 having the same dimension, then 4 to 8, 4 to 7, all the dimension are same. So that's why we have divided the number of 11 number of panel case. So if you find out, if you sum all the cases, there. So here this 1 to 4 panel, 2 panel of 2500 mm, 4 panel of 3 to 50 mm, and 5 panel of 3.6 meter. So we sum all these, it will come 36 meter. It will come 36 meter. So that's why they have divided the my plate girder into number of panel. to get advantage of it behave uh, uh, like a like a truss. Okay, so that's why we are going for that. So diagonal tension and diagonal compression will be in case of this we will come into picture. So we'll see how it will be possible. So here I will take for my calculation first. I will take the panel number one. What is the panel number one? That is ABCD. ABCD is my panel number one. So I will take the first panel. Consider panel number one. Consider panel one. That is panel one is, you can see, is ABC. A B C D. Having the center to center distance of this stiffener is 2500, and depth, you know, it is 2600, plus thickness of flange both sides is 50 mm. Okay, so overall depth of girder will be 2700. Okay, so this we will consider for the panel number one. So we'll check how the panel number one is designed. Okay, so stiffener spacing here is C is equal to 2500. 2500. Okay. Now, shows the symmetrical arrangement. That is already we ordered symmetrical arrangement. So this figure shows the symmetrical arrangement, half part of the plate girder with the stiffener spacing. Okay. Now resistance to shear buckling for stiffened plate girder is obtained as per clause 8.4.2.1, page number 59. So we have to D by TW ratio, we have to find out. So if you go to page number 59 of IS code, this is the IS code. This is our page number 59. Okay, page number 16, page number 59. So here simple post critical method, and so here resistance to shear buckling 8.4.2.1. Resistance to shear buckling shall be verified as specified when D by TW ratio should be greater than 67 if epsilon for the wave without stiffening. Okay, or D by TW ratio greater than 67 out of kV for 5.35 for a wave with stiffener. So here we are going with the stiffener. Here we are going for wave with the stiffener. So here you can say what we will take D by TW ratio. So we have find out D by TW ratio, and we have to take this uh, as our case, which this we have to take our case because we are going for the stiffener. So we can write down D by TW ratio greater than 7 E under root of kV upon 5.35. So I will write down. Then we going for the panel number one. So here D by TW ratio will be greater than 67 E under root of kV upon 5.35. Okay, this is from the clause 8.4.2.1. 8.4.2.1. Okay. So D by DW ratio already we have find out, that is 162.5. 162.5. Okay. So you can find out the value of your kV. Okay. So D by DW ratio, so 67 into epsilon is 1 under root of kV. That kV is the shear buckling coefficient. Okay. So shear buckling coefficient, that kV is, see the following calculation. So you can find out the kV from the IS code itself. So in IS code it is given how to find out the kV. So here in clause number this uh, on page number this 60, you find out the kV. This is kV you can find out. When kV is equal to 5.35, when the transfer stiffener are provided only at support. तो यहाँ पर तो हम लोग मिड में भी प्रोवाइड कर रहे हैं. Now based on C by D W ratio, you can find out the kV. So C by D W ratio C by D ratio, C by ratio, that is 2500 upon 2600 is 0 point something. So 25,000 divided by 26. So it is 0.96, 0.96, which is less than 1. So you can find out kV value by using the hash code. kV is equal to, because C by D ratio is less than 1, so we will use this formula 4 plus 5.35 divided by C by D square. So I will write down 4 plus, so kV is equal to 4 plus 5.35 divided by C by D square. Okay, so from this IS code we can find out this value. So C by D value already we have calculated. So square of that is 0.92, so 5.35 divided by the answer, that is 5.786. So it is coming plus 4, so 9.78, 9.786, or you can approximately write the kV value is 9.8. So we can find out kV value like this. So this kV value now we know. Okay, so we can find out the kV. So 67E. So this side, if you will write down, so D by TW ratio is 67 into epsilon is under root of 250 upon 250. 250 upon Fy. Fy is a 250. So 250 upon 250 is 1. Okay. Into kV we have found out. Under root of kV is 9.8 divided by 5.35. So you solve this, so 9.8 divided by 5.35 under root of that value into 67. So it is coming 90.67, 90.679. So here DY/TW ratio is greater than that, so stiffness are required. So you can say here just 90.67 where is coming. So now this we wrote out. Now we go for the tau CRE, elastic critical shear stress of the. Okay, so here that condition satisfies that condition. Here it is given for shear buckling check is required. This condition V by TW ratio is greater than this value. So condition here satisfied with the stiffener, so we have to check for shear buckling. Okay. Now we will use the simple post critical method, and now we have to find out the tau b. So VCR is equal to AV into tau b. So you find out the tau b. To find out the tau b, you know lambda w, you know tau CRE value. Okay. So all this value you have to calculate. So first we will go for that. Okay. So tau CRE is the elastic critical shear stress of the wave. So this formula is given as code. No need of remembering anything. So reverse calculation in the tau CR is the elastic critical shear stress. It is already given here. Just you have to put the value. Just you have to value. Use the Poisson ratio. Poisson ratio which still is given in page number 12. That is point. You can go here on page number 12. The Poisson ratio is given already in your IS code. Okay, so this Poisson ratio of steel is 0.3. So 0. Here mu Poisson ratio is 0. Okay, so likewise you can go ahead and so mu here, mu is here. Poisson ratio is uh, 0.3. Okay, d by tw ratio we already know. Kv pi square we already all this value you know. Put all this value, put all these values in this formula. That is tau CRE. Tau CRE is Kv pi square. So tau CRE or TCR you can find out Kv pi square. Okay, divided by 12 under in bracket 12 in bracket 1 minus mu square into d by tw square. 2 d by tw square. I think so. This is the formula. Put all the value. You will get tau CRE 67.08. Put all the value. Now you know here. Here you know the kV. kV we have find out 9.8. Pi value you know. E is 2 into 10 raised to pi for the steel. 12. 1 minus mu square is 0.3 square into d by tw ratio is 162.5 whole square. We will get this tau CR value 67.08. Okay. So this first step we have done to find out the VCR. So tau CRE we know now. Now tau CRE we know, you can find out lambda W. So lambda W is equal to under root of lambda W is equal to under root of under root of under root of FYW under root of FYW divided by under root 3 into tau CR. Root 3 into tau CR. Okay, this is formula. Okay, so this formula we have find out. Put the value and you can get the tau CR value. So tau CRE we have already calculated here, that is 67, and FYW is the yield stress of web material. So FYW generally we are taking as 250. Okay, root 3 into 67.08. So if you solve this to 67, that is under root of 3 into 67.08, 250 divided by that answer. So it will come in under root of 2.15, and if you remove the root, it is 1.466. So lambda W now you can find out. Lambda W is you find out. Now you know the lambda W. So lambda W you know. So lambda W is in our case 1.466. Okay. So lambda W in our case is 1.46, which is greater than 1.2. So here in case of I square you can see the different formula to find out the tau b. So when lambda W is less than equal to 0.8, then you have to use this formula, first one. When lambda W is between 0.8 and 1.2, you have to use this formula to find out tau b. But here the lambda W is greater than 1.2, 1.466. So here you can write down here lambda W is greater than 1.2. So we are going for the formula tau b is equal to FYW divided by root 3 into lambda W square. Okay. So I will use tau b is equal to FYW divided by root 3 into lambda W square to square. Okay. Lambda W square. You know the values. FYW is the stress of this root 3 into 1.466 square. So you can find out the tau b. So you calculate this. Okay. Into 250. It is coming 67.08 again. tau b is coming 67.08 Newton per mm square. Okay, maybe some calculation it will be changing. Now we can find out the VCR. So here you can see uh, for the simple post critical method, we are going for the simple post critical method here. Huh? Like, so always when you are going for design of your panels, so first you will check in the simple post critical method. If that VN that here the VCR will be very safe, then we don't need to go for the tension field action. Okay. So here VCR is equal to AV into tau B. I will write down here. VCR is equal to CR is equal to AV into tau B. tau B हम लोग ने कैलकुलेट कर लिया सिंपल पोस्ट क्रिटिकल मेथड से. Now AV, you know, AV is the shear area. Shear area is nothing but D into TW. D into TW. Okay. तो D हमारा कितना है? That is 2652600. और TW अपना thickness of this क्या है? 16 mm. So I will write down. That is D is 2600. TW is 16. So I will write down all the value here. VCR is equal to 2600 mm into 16 mm into tau b is 67.08 Newton per mm square. So this will be coming into Newton. So 2600 into 16 into 67.08. So this is coming 2790528 Newton. If I write down, it is 27905 point 2709.530 Newton. So what is the shear in our case? In shear in our case is 2310. So this value is much greater than 2301 kilonewton. So our this VCR, now this is, we will not compare with this because we are not taken the partial safety factor. Now now we can find out the VD. VD is equal to VCR divided by gamma MO. Okay, so VD is equal to VCR or VN upon gamma MO. So I will write down here. Sorry for that. So here we can find out equal to VCR or VN, whatever you can say. So 2790.53 divided by 1.1, so it will come in 2536.84 kilonewton. Now this we can compare that our design shear stress is design shear is greater than the factored shear, and factored shear is 2301 kilonewton. So it is much larger than that. So we can say that. So this is our panel A or panel 1, panel 1, panel 1 save for spacing of stiffener. Stiffener C is equal to 2500. Okay. Now since you can see that since this here it is safe, then no need for tension field action, tension field method. Okay. So in simple post critical itself, our design is safe. Okay. So in this panel number 1, no need of going for the further चलो समझ में आया यहाँ तक. So this is nothing but you can so this is in our case we have checked. समझ में आया. Therefore, end panel will not be checked for the tension field action because it is the shear VD is because VD is because VD is greater than VD is design shear is greater than factor shear. Now only we have checked one panel. Similarly, you have to check all the panel. It is not necessary you will go all the panel, but as you proceed, you come to know that कि कौन सा panel safe आएगा, किसमें problem आएगा. So there are some in some panel there is maybe the concentrated load over that. So that also we have to check for the shear. Okay. Now we will go for another panel. So I will take the another panel here. In our plan, you can say the second panel. Second panel is BEFC. Second panel is we can see take the second panel that is BEFC. So I will write down. Now take panel number 2. Okay. Panel 2. Take now panel 2 that is BEFC 3 C is equal to 3250 m. C is equal to 3250 m. Okay, तो यहाँ पर आप देखेंगे C की वैल्यू 3250 m. Now you can find out C by D ratio is C by D ratio. C is 3250, D is 2600. It is coming 1.25, which is greater than 1. So here kV value you can find out based on that. Now it is changed. The kV value you can find out. The formula will change because C by D ratio is changed. So you can go for the C by D ratio. So you can see here C by D ratio in shear buckling number 59. You can see here. This you have to find out, so you have to go for that. So here in simple post critical method you have to find out the kV how to find out, because C by D ratio is greater than or equal to 1, so this formula you have to use to find out the kV. So kV you can find out kV is equal to 5.35 plus 4 divided by C by D square. This is the formula as per the I-score you use. Okay. 5.35 plus 4 C by D. Now here I will write down 5.35 plus 4 divided by 1.25 square. So if you calculate this, so 1.25 square, 4 divided by answer plus 5.35, it is coming something 7.91. 7.91 is the value of kV. Okay, so kV is 7.91. Okay, so in our case also here also. Now again you have to find out tau CRE. Again you have to find out tau CRE. So tau CRE, you know the formula, pi square E, kV cos square E divided by 12 1 minus mu square, 12 times 1 minus mu square, mu is the Poisson's ratio, into D by TW whole square. So K is 7.91, pi square, you know the value, and then E is 2 into 10 raised to 5, and 12 1 minus mu and 1 minus 0.3 square into 162.5 whole square. So we can find out tau CRE here. Tau CRE will be 54.24 here. 54.25 I'm not wasting time for the calculation. You can check it. If there is some correction, you can do. Okay. Now lambda w is nothing but lambda w is nothing but under root of fyw upon under root 3 tau tre. So this lambda w, if you find out, it is coming 1.63. Again, 1.63 is greater than 1.2. So you can go for the tau b is equal to this formula. Tau b is equal to fyw under root of root 3 into this lambda w square. So tau b is equal to fyw divided by root 3 into lambda w square. Will give the tau b value, and tau b value it is coming 54.25 again. 54.25 Newton per millimeter square. Now you can find out the VCR. VCR is equal to AV into tau b. Okay, AV you know 2600 into 16 is the AV. This is AV, and tau b 54.24 Newton per millimeter square. You can find out the VCR. So 2600 into 16 into 54.24. It is 2256.8 kilonewton. Okay. Now VD is equal to 2256.8 divided by gamma MO. Gamma MO is nothing but 1.1. So divide this by 1.1. It's coming something 2051.6 kilonewton. Okay. Now at the end, this panel, you have to calculate the shear. So shear at point B you have to calculate. Shear stress at point B. पॉइंट ए से शेयर रिड्यूस हो जाएगा, है ना, मैक्सिमम शेयर रिएक्शन पर रहता है, तो ये रिड्यूस हो जाएगा. कितने से रिड्यूस होगा वो हमको मालूम करना पड़ेगा. तो 2301 माइनस, है ना, कितना लोड आएगा 29 पॉइंट कितना था हमारा here at the 29.5. The last panel theta is 2.5. Yeah? So this 79.5 UDL into crystal is 2.5 meter. This is the last panel length. Okay. So it will give the shear at the point B. So maximum shear at point B. 79.5 into 2.5. Okay, 198. So 2301 2102.25 kilonewton. Okay, so shear at B you can calculate 2102.25 kilonewton. So now here you can see that this value ED in case of simple phase critical method, in case of panel BEFC, fails in simple post critical method because VD is less than VU. This is your VU at point B. VU at point B. So this value is greater than the VD value. So VD हमारा कितना है 2051, which is less than 2102. है ना. इसके लिए now you have to go for tension field action. So here, in this case, tension field action is required. Tension field action is required. So from here, so as shear buckling resistance is less than factor shear at B. So you can write down as 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 shear buckling, shear buckling resistance, shear buckling resistance VD is 2051 kilonewton, which is is less than less than factored shear at factored shear at B, at point B where it is maximum shear, so that tension field action takes place, so that tension field action will takes place. Okay, now this tension field action takes place, and uh, so for another class, we will continue this problem example in this your practical class coming at 11:10. ओके 11:10 को जो आपका प्रैक्टिकल क्लास है उसमें हम लोग ओके कंप्लीट ओके। तो अभी यहाँ तक मेरे ख्याल से सबको समझ में आ गया होगा, और मैं फिर यहाँ से फ्रॉम हियर विल मार्क द पॉइंट, फ्रॉम हियर विल गो फॉर द टेंशन फील्ड एक्शन। ओके, तो टेंशन फील्ड एक्शन इससे पहले भी बताया कि the capacity of section will not end here in simple twisting. Okay. Due to tension diagonals, the capacity of by providing the stiffness, it is increased. No failure will occur. Okay. Some deformation in the plate, and that will be controlled by the stiffness. That will be controlled by. So this design with the tension field action we'll see in the coming class. So we'll stop here. So we have another class. If you don't have class, then say me, I will continue. Okay, or otherwise if there is class, so we'll stop. Okay, समझ में आ रहा है आपको? आपको समझ में आ रहा है कि okay, no issue. So we will